Okay. Um, so good afternoon, everyone. I had postponed this session for some personal reason. So welcome all to live session 11. I hope I'm audible. Let me just check. Yeah. So good afternoon, everyone. Welcome all to live session 11. Now, what we will do today? Uh, Today also we will spend some time on weldability, right? So we will spend time on weldability of structures like um, low alloy steel, high strength low alloy steel, then heat treated alloy steel, and yeah, so mostly we will spend some time on those materials. So in our previous class, we had discussed on this carbon steels, right? So mainly we discussed on this low carbon and medium carbon steel. So today, initially, what I have planned is we will spend some time on high carbon steel first, and then we will move to this alloy steel, right? So first, we will discuss on high carbon steel. So because my tab is not working, as I said in my earlier classes, so today also I will be using this PowerPoint mode. So please bear with me on that regard. And yeah, so initially we will talk about this high carbon steel, right? High high carbon steel. So what can we think about high carbon steel, or what should be the content of carbon, right? Yeah. Mainly that should come first. What should be the carbon percentage in your high carbon steel? So high carbon steels include around point 0.3, around 0.3 to 0.5%. Okay, so this is medium carbon steel. This is medium carbon steels. And for high carbon steel, this is around 0.5 to 1%. Okay. Now, welding of high carbon steel is difficult, or this is much easier than the low carbon steel? So if you think of welding of high carbon steel, that is much more difficult than welding of if your steels are having lower carbon content. Why? Because because high carbon steels will have greater tendency of martensite formation, right? So this high carbon steel will have martensite formation tendency. This is much higher. Okay. So because the tendency is much higher for martensitic formation in your heat affected zone, uh, we had talked about in our earlier classes regarding hydrogen cracking, right? So if my martensitic formation tendency of this is much higher, so the cracking tendency also will be higher. So hydrogen cracking, denoting is as H2 cracking. H2 cracking is much higher for this high carbon steel, right? Now, yeah. So we had talked about this base metal microstructure in our earlier classes, right? What will it consist of? The base metal of any kind of steel. Initially, it will be consist of ferrite and perlite, right? So if we do some etching, chemical etching, you will see different contrast of in your microstructure. One will be light etching, one will be dark etched, right? So the light etching portion, so you should know about this. The light etched portion, that will be ferrite. So I will denote it as alpha ferrite, and and my dark etched portion will be what? Dark etched portion will be perlite, right? So that is there. So initially my microstructure is consisting of these two phases. One is perlite, one is ferrite. Am I audible?
Yes, sir.
Yeah. Okay. Sorry. So yeah, we have this light edged portion and dark edged portion of ferrite and perlite. And as I said in my earlier classes, that uh, you can differentiate different regions in your steel weld structure, right? So there is this three different regions. Uh, we had talked about. Let me take this one. So we had talked about. Let's say this is my cross-sectional view of this weld metal structure, and over here this is fusion zone, right? And this is heat affected zone. So I can differentiate at four different regions over here. Let's say this is A, location B, location C, and location D, right? So what will happen at position B to D? So these different regions are, one is partially grain refined region. This we had talked in our earlier classes. Uh, One is this partial grain refined region. I am making some abbreviation. Please note those things. Grain refined regions. One is partially grain refined regions. Then grain refined, and finally you have grain coarsened region, right? You have three different regions at uh, for your weld microstructure. Now in the grain coarsening region, which one is the grain coarsening region for this four different positions? So position D is the grain coarsen region, है ना? Which is the most vicinity of your fusion zone. So over there you will experience high cooling rate or low cooling rate. In terms of cooling rate, over there, because the temperature will be much higher, because in that is in the vicinity of fusion zone, right? So it will experience higher cooling rate. My position D, it will experience, so CR is cooling rate. Please remember these abbreviations, or you can note these abbreviations. So cooling rate will be much higher for position D, right? And even the grain size also will be large over here. The grain size is also large for position D. And because of those things, it will promote formation of martensitic formation, right? So tendency, martensite formation tendency will be much higher for position D. Agree? Now, on the other hand, if you have some lower cooling rate, if you have lower cooling rate and smaller grain size, what that will encourage, what kind of microstructure it will form. It will form perlite and ferrite kind of microstructure, right? I know. Now, because of formation of martensite, I told that there are two different strategies. If we want to reduce the amount of martensitic formation, either we can do preheating, something called preheating. One is preheating, and another is called, one is this control of interface temperature. If we can do some interface welding and you can control those interface temperature, there will be this dissolution of carbon with higher temperature, and it can reduce the tendency to form this martensite, right? So uh, this control of interface temperature. Any question? Now, if your plate is much thicker, let's say you have two different plates, one is 5 mm thick, one is 10 mm thick. Which one will require more preheating? So for thicker plates, more preheating is required because for a given heat input, the cooling rate is higher in a thicker plate. So I will note it down. So thicker plate, thick plate, more preheating. Why? Because for same heat input. So if my heat input is same, cooling rate is much higher for thicker plates, right? Now, in addition to higher cooling rate, uh, your thicker plate will have slightly higher carbon content also, in order to ensure some proper hardening during heat treating step of steel making process, right? So that is also the reason the preheating will be required much higher for thick plates, high carbon content also, high carbon content, to ensure proper hardening. That I'm not writing, so please note it down. So thicker plates will be required more preheating, as simple as that. Okay,
Okay, sir.
right? So
Yes.
over here, mm, if we have something on this carbon steel, this is one question from carbon steel. Once those are over, we'll move to this low alloy steel. So feelers for high carbon steel welds are chosen based on the consideration of what, uh, will those high carbon steel will be chosen on the consideration of dilution of carbon, or how those steels are responding depending on your temperature and time during your heat treatment process, or the carbon pickup percentage, or which one? So the basic sense will be all of these will be important for choosing your feelers, right? So if your carbon for high carbon steels, how the carbons are getting diluted in your steel material, how the carbons are reacting for your heat treatment process also, what is the composition of carbon pickup, all of those things will be required to understand what should be my feeder metal, right, while during consideration of this high carbon steel. And then question 3 asks that medium carbon steel joints designed for impact loading So for impact loading case, medium carbon steel joints are designed. Uh, they are generally subjected to what? If you want much higher impact loading. So if you are considering impact loading,
Like
what kind
toughness,
of
it
it
required
should
more
high
toughness.
toughness, exactly right. So it
Yes,
should
sir.
require high toughness. Which one will be beneficial for higher toughness over here?
Oh, post well treatment, high cooling rate, low solidification time,
So high
high
cooling rate, low solidification time, all of will contribute to your martensite formation, or basically uh, more carbon will be there. More carbon means it will be more hard, more brittle. So you want to relieve stresses, right? So post-weld heat treatment will be required for
yes, sir.
if you want to enhance your impact loading over here, right? Agreed? Okay. Next. Uh, so one is this: arrange the following in increasing order of their cooling rates used corresponding to different transformation phases. This you can answer from your iron carbon phase diagram only. So which one is true in terms of increasing order of the cooling rate?
Martensite, ferrite, benite, ferrite.
Uh, so if I say over here, three.
Increasing order of their cooling rate used corresponding to different transformation phase. 4340 ST.
So the common part is martensite is having highest cooling rate, right? So if your cooling rate is much higher, if you think of this CCT diagram or temperature time transformation diagram, you had this upper critical temperature, then you had those nose over here, and then you had those martensitic start and martensitic finish temperature, right?
Yes,
Initially
sir.
we'll be starting from austenite. So let's say this is austenite, and if I cool it so fast so that it will not go beyond this limit, so it will form martensite. So martensite is having much higher cooling temperature. So A and B are screened from here. So both of these are having higher cooling rate, and from there, if you cool little, so your cooling rate is little slower than the martensite. Over here it will form what? Benite, and with further reduction in cooling rate, will form those ferrite and those fine perlite and coarse perlite structures. So much slower. Over here you will form coarse perlite. Over here you will form fine perlite. Then ferrite. Over here you will form benite. So please refer to that CCT diagram. And over here it will form martensite. So which one will be true? 5. 4. So if you ask me, B will be correct option over here. Okay.
Yes, sir.
Okay. Let's move to this alloy steel then. Then we will go through the questions again. So we will talk about now something called low alloy steel. Okay. Three major types of low alloy steel. What we will be discussing right now. There are this high strength low alloy steel, high strength low alloy steel. Please note this abbreviation, high strength low alloy. One is quenched and tempered low alloy. So quenched and tempered low alloy steel. And finally, one is heat treatable low alloy. Heat treatable low alloy steel. So these are three different kinds of low alloy steels we will be talking right now. If you think about this HSLS steel, high strength low alloy, they are designed to provide higher strain than those of carbon steels always, right? So high strength low alloy steel strength will be higher than carbon steel. Okay. Now, so what alloy compositions we add for this high strength low alloy steels? So we add manganese, we add silicon, as in carbon steels also. Now, for HSLS steels, high strength low alloy steel, they contain very small amount of niobium, vanadium, and titanium also, right? So manganese and silicon are always there. Manganese and silicon for this alloying option. This is similar to carbon steel. Along with this, for high strength low alloy steel, you will have niobium. I'm not very sure of what was the percentage. So you please refer to any book or Google. Niobium will have niobium and vanadium also, and titanium, right? They will be in terms of very small percentage, of course. So they must be less than 1%, even not 1%. They will be in the range of some point 0.05 to 0.07. So in that percentage, people do this alloying for niobium, vanadium, titanium to ensure. So they are grain refiners. These alloying elements. So in high strength low alloy steels, we add these alloy elements to ensure both grain refinement. One is this grain refinement and precipitation hardening. So again, I, I will note this precipitation. I will write only precipitation. Fine. Precipitation hardening. Yeah. So two for these two aspects, these alloying elements will help in terms of precipitation hardening and grain refinement. They are also called microalloy steels also. As I was saying that the alloy compositions will be very small, very small. So they always will be in the range of 0.05 to 0.07% probably. Uh, they also are known as microalloy steels. Okay. Now this niobium, vanadium, titanium, they are strong carbide and nitride formations. Remember that. So these alloying elements are strong carbide or nitride former. Fine. Now, if they are strong carbide and nitride formers, so basically it will form fine carbide or nitride particles, right? So carbide and nitride particles of these metals, niobium, vanadium, and titanium, what they will do, they will tend to hinder the movement of grain boundaries. So as you know, if they want to hinder the movement of grain boundaries, there will be reduction in grain sizes. So there will be strain hardening, right? So you know that, you know. So if these carbide and nitride particles are hindering the movement of grain boundaries, it will help me to reduce the grain size by making grain growth more difficult. As simple as that. Now, this reduction in grain size for this HSLS steel, what they will do if there is this reduction in grain size? So there is something called Hall-Petch relation. Not going into very details. So remember this thing, Hall-Petch. Remember this name only. So there is this relation of sigma equal to sigma naught. I also forgot exactly sigma naught. Into d to the power half, something like that. So this is proportional to square root of grain diameter. D is grain diameter, right? As you refining, uh, no, sorry. Let me check once. So what I will do, all fetch relation. Can you see the screen?
Yes, sir.
Yeah. So see, Hall-Petch relation is this: sigma y equal to sigma. Yeah. So this is inversely proportional to d to the power half. So if you are reducing your grain diameter, more fine, more refinement in your grain structures, it will increase the yield strength of your metal, right? So that's what I was talking about, Hall-Petch relation. Should I write it down? Sigma y equal to sigma naught plus k d to the power minus half, right? So just remember this Hall-Petch relation. It will tell you that uh, it will give you the relation between yield strength and the grain diameter. So more refined grain structures, more fine grain structures, yield strength will be much higher, right? Okay. So so uh, yeah, that will increase the strength and toughness at the same time. The reduction in grain size. Now this is interesting because normally the toughness of steel that decreases as their strength increases. है ना? So if you are increasing your strength, you are compromising the ductility, you are compromising the toughness. But over here, this is interesting that it will increase the both strength and hardness at the same time. So among the carbides and nitrides of niobium, vanadium, and titanium, which one is most stable? So people have seen through research that titanium nitride is more stable. Okay, titanium nitride is titanium nitride is more stable structure. So it has smallest tendency to decompose and dissolve at higher temperature. So usually what is done for precipitation hardened metals, more you provide temperatures, there will be tendency to dissolve of those precipitates. You know? So titanium nitride is much more stable. It will have smaller tendency to decompose and dissolve into high temperature. So remember this also. So yeah, because of that, titanium nitride makes it most effective in limiting the extent of grain growth in welding in terms of in comparison to this niobium, vanadium and titanium carbides and nitride formers. Titanium nitride is the more stable structure, right? Now if you provide higher heat input, so if your heat input is much higher, for higher heat input during welding, so more likely, so if you're not thinking of titanium nitride, more likely those carbide and nitride particles will dissolve, right? And they will lose their effectiveness as grain growth inhibitors. So with temperature, uh, carbide and nitride particles will dissolve, and because of dissolution they lose their effectiveness as the inhibitors, as the grain growth inhibitors, right? Now, yeah, now it has also been reported in earlier literatures that if your steel, if it contains titanium oxide, if your steel contains titanium oxide, Ti2O3, so these things, whatever I am just mentioning over here, I'm taking it from some book called you can refer this also if you have some time. So the book name is Welding Metallurgy by Shindo Ko. You can refer this book. This is a very good book for uh, whoever wants to initialize, or whoever wants to some fundamentals on this metallurgical aspect. You know? Now, uh, yeah. So you are talking about this titanium oxide. They will tend to have better toughness. So titanium oxide is more stable than titanium nitride, and again, it will not dissolve even at higher heat inputs. So they do actually stop grain growth, but act as effective nucleation site. So they will act as effective. And you understand this handwriting? I'm not sure. Uh, This is very
Yes, sir.
complicated to control the mouse.
Yes, sir. Yes, sir.
Okay. So this will be effective nucleation effective nucleation site for ferrite structure. Next. So if you see this high strength low alloy steels, uh, they are usually welded in the as rolled or some normalized condition. So people do normalizing, right? Heat treatment, normalized in heat treatment. So either either they do welding in for as rolled condition, or they can do some, if you have done normalized heat treatment, if that will also be done for this high strength low alloy steel. And the weldability, so if you're thinking of this weldability of HSLA, this is more similar to mild steel only. That also please remember. So this is much more similar to mild steel. then strength is often predominant factor in your application of high strength low alloy steel. Uh, During welding, if you are uh, using any kind of filler metal, that is often selected on the basis of matching the strength of your base metal, है ना? So because you want strength in your structure, so that's why we don't compromise on your base metal strength. So what people do, they choose, if you're using any filler metal, they choose the filler metal similar as what you are using as base metal. Now over here, preheat and interpass temperatures that will be required are relatively low than what we are talking during high carbon steel. So over here, preheat temperature, preheat and interpass temperature are relatively low. Okay, any question?
No,
So
sir.
amount of preheating will be amount of preheating that will be required, that will increase with increase in carbon content, or that will decrease with increase in carbon content. So the amount of preheating I was talking about, initially I was talking about the steel thickness, right? So with increase in thickness, with increase in carbon and alloy content, the amount of preheating required also increases. Okay, so if your thickness increases, sorry, I've got cold. So if your thickness increases and if my carbon content also increases, even the alloy content, whatever you be alloying with your metal, so if those increases, the preheating required also increases. Now this remembers me, one question was there. So this I just stopped right now. So can you tell me which one will be the correct answer for question 10?
Yeah, sir.
Which one?
Minimum 8 seconds, sir. Both minimum preheat temperature and temperature decrease. Interpass temperature. ऑप्शन ए टेम्परेचर इंक्रीज होगा यदि थिकनेस अपन इंक्रीज कर रहे हैं तो
So with increase in intersection thickness of steels to be welded in general, uh, this minimum preheat temperature and interface temperature, that will increase or decrease. I
मिनिमम
told
प्रीहीट टेम्परेचर इंक्रीज
increase. So both minimum preheat temperature and interface temperature both will increase with increase in
ओके
section thickness. Okay,
ओके सर
C is true, and even this is true for increase in carbon content, increase in alloying content also. Increase in carbon and alloy compositions.
थिकनेस इंक्रीज अल्फा कार्बन कंटेंट इंक्रीज
Right. Okay.
यस सर
Okay. So next we'll move to this QTLA, quenched and tempered low alloy steel. Okay, I can finish this also. This I have already mentioned. Darker parts in the following optical microscopic image of carbon steel at some magnification. Darker one. So I was talking about light etched region, dark etched region. So if you do this etching in your steel, structure, you will see these kind of microstructure. One is dark edged, one is light edged. So the darker parts are which one? The darker parts are perlite structure, these black ones, and the light edged region is the ferrite portion. Okay, remember that. So the dark edged region is perlite, and light edged is ferrite, right? Okay. So next we'll be talking about quenched and tempered low alloy steel. So this quenched and tempered low alloy steels, they usually contain less than point uh less than 0.25% carbon, I think so. So 0.25% carbon, less than 0.25% carbon, and less than 5% alloy contents. Right? So what is the mechanism of their strengthening? The mechanism is primarily by quenching and tempering to produce some microstructures that will contain martensite and benite. Okay. Now, low carbon content is desired in such alloy for two reasons. Low carbon content is desired. So I mentioned less than 0.25 na. So low carbon content is desired. There are two reasons over here. What are those two reasons? One is minimize the hardness of the martensite that it will form. So minimize hardness of martensite. This is one. Another is you will have this martensite start temperature, right? So low carbon content is desired to raise the martensitic start temperature, to raise the MS. So I have denoted the martensitic start temperature as MS, as denoted is in normal time temperature transformation curves. If you see time temperature transformation curves, MS is denoted as martensitic start temperature, MF is denoted as martensitic finish temperature, right? So low carbon content is desired to raise those martensitic start temperature so that any martensite that will be formed that can be tempered automatically during cooling. So what is the mechanism? Tempering automatically during cooling. Okay, that will also reduce the or minimize the hardness of the martensite or brittleness if anything is forming there because of martensitic transformation, that will get reduced because you are relieving the stresses, right? with the
Yes, sir.
question. Now, if you are forming this low carbon auto tempered martensite, I'm calling it low carbon auto tempered. So, because I'm raising this start temperature, the temperature will be high enough to to do this tempering at higher temperature during cooling. Now, due to the formation of this low carbon tempered martensite, I will obtain both high strength and toughness. Both strength and toughness will be obtained due to this kind of, if you are scheduling your heat treatment in such a way that uh, you'll form both higher strength and good bit of toughness in your structure, even though you are forming martensite over here. Now, in terms of alloying elements, you can add manganese as was as it was there for carbon steels also. Along with that, you can add chromium, nickel, and monel. These are my alloying elements to ensure the hardenability of such alloys. Now, over here, over this alloying composition, whatever I'm mentioning right now, this manganese, chromium, nickel, and monel, if you use this nickel, the nickel content, if you increase the content of nickel, that will increase the toughness and that will lowers the, there is something called ductile brittle transition temperature. I'm not going into very detail of that, but remember this term, ductile to brittle transition temperature. So as the name suggests, there will be some transition temperature after which your ductile metal can treat it as brittle material. Ductile to brittle transition. So you can, I can remember the story of Titanic. You can read that. So this was some failure due to ductile to brittle transition of the steel what was used while Titanic was fabricated, right? So that design consideration was not considered during that time. So ductile to brittle transition temperature also is very important for your steel metals. That is there. If you're interested, you can just check. Now, yeah, as I was talking, this manganese, chromium, nickel, and monel that will ensure the hardenability of those alloys. Now, um, yeah. Now, in terms of welding processes, you can use any common welding process what you can think of. So, be it TIG, MIG, or whatever is with you, maybe shielded metal arc also. But what what thing is to be considered is the weld metal hydrogen, the hydrogen content that must be maintained at very low levels. So hydrogen content, hydrogen composition or hydrogen percentage should be low enough. Okay, so that must be maintained at very low level. Uh, and as I have mentioned again and again that preheating is required, if you want to prevent those hydrogen cracking. So preheating and interface temperature required. Uh, yeah. So preheating and interface temperature, this is required higher than this HSLA. So preheating and interface temperature is higher than HSLST. However, if you provide too high preheat temperature or interface temperature, what will happen if you provide it very high? That is also undesirable. So preheat temperature or interface temperature, very high temperature of those, it can decrease the cooling rate of your weld metal, right? So cooling rate also will decrease, and uh, there will be this transformation of your austenitic structure to either ferrite or coarse benite based on what is your cooling rate. Both of those lack high strength and good toughness. So this preheat and interface temperature should always be optimized, right? So that it will not form more martensitic, it should not form more ferrite or benite, right? There should be some synergy in between those strength and ductility of your structure. Okay. Any question?
No, sir.
No. Okay. Okay. So we have talked about this quenched and tempered low alloy steel. Now I was talking about this higher post weld means disadvantage of higher post weld and interpost temperature, right? Post weld, not post weld, higher interpost temperature and higher preheat temperature that will decrease the cooling rate. If you have excessive heat input, if your welding is having excessive heat input, that will also decrease the cooling rate, right? So excessive heat input also reduces your cooling rate, right? That also will produce some unfavorable microstructure and some unfavorable properties, right?
Yes, sir.
Mhm. So next we'll be talking about, if you have no question, we'll be talking about this HTLA, heat treatable low alloy. So what is heat treatable low alloy steel? So usually it is referred to medium carbon quenched and tempered low alloy steel. Okay, medium carbon QTL steel. That is also known as heat treatable low alloy steel. So what will be the alloy content? Typically, my alloy content will be up to 5%, and carbon content will be a little higher than what we were talking for this quenched and tempered low alloy. So over here, carbon content will be 0.25 to 0.5%, medium carbon. Okay, and alloy composition is till 5%. Now, what is the strengthening mechanism over here? Here also, your structure will be strengthened by quenching, right? For uh, that quenched and tempered alloy steels like that way. Over here also, the strengthening mechanism is quenching to form this martensite and tempering it to the desired strength level. It's just that the carbon content will be higher than the uh, QTLS steels, right? So quenching and quenching and tempering is the primary strengthening mechanism for strength, for increase your strength to desired level. Now, the higher carbon content, what they will do if you are having higher carbon content in your structure, will your hardness will be higher or lower?
Higher, sir.
So if I having higher carbon content, it will promote higher hardness level and lower
Higher
toughness,
strength. Hmm.
right? Higher strength and low toughness.
Yes, sir.
So there will be greater susceptibility to hydrogen cracking always than the quenched and tempered low alloy steel that I have talked just before, this HTLS steel. So strength is strength, or I will say it hardness is higher, toughness is lower. So H to cracking tendency is much higher, right? I have some thoughts here. Now, this HTLS steels, how you can weld those HTLS steels if they are having higher carbon content? So you are talking about this high carbon steel also. How can we do this welding of HTLS steels then? So they are normally welded in annealed condition or over tempered condition, right? Uh, Except for weld repairs. So if you are thinking of weld repairs, it is usually not feasible to anneal or over temper the base metal before welding, right? So except weld repairs condition, HTLS steels are normally welded in the annealed or over tempered condition. Okay, so annealed or over tempered condition is provided for welding of those HTLS steels. And uh, immediately after welding, the entire weldment is heat treated. So what it will do, it will reoptimize your structure and then quench and temper to the desired strength level, or at least you do some stress relieving or tempering to avoid hydrogen cracking. So these are normal sequence of imparting your strength and toughness in your the heat treated low alloy steels, right? So what we will do, immediately after welding, we will do the heat treating of the entire weldment. That is, we will reaustinize our structure. Welding, then Reaustinize by heat treating and then quenching and tempering to the desired strength level. Quenching and tempering to, you can understand the right up, right?
Yes, sir.
Okay, quenching and tempering to desired strength level, or at least you can do some stress relieving to avoid hydrogen cracking. Over here also, any kind of common welding process you can think of, you can use this common welding process that can be used for welding of these HTL steels. Now, to avoid hydrogen cracking, because this is more prone to hydrogen cracking, the weld metal hydrogen must be maintained at very low levels, right? So, because of that, as I was saying, again, proper preheating and interface temperature must be used, right? So for HTL steels also proper preheating and interface temperatures that must be used.
Yes, sir.
So preheat and I will, what I will do is preheat temperature. I will just mention preheat temperature to reduce cracking tendency, right? Now, yeah, and this preheat temperature, uh, for particularly for this heat treated low alloy steel, I will say this preheat temperature that must be maintained after welding also, after welding is completed also, sorry. So even after welding, this preheat temperature must be maintained. This, so basically we'll do some post weld heat treatment also. So this must be maintained even after completion of welding. Now in applications where your weld metal will be required to respond to the same post weld heat treatment as the base metal, in order to match the base metal in strength, if you are using filler metal, that will be, you will be using similar metal of the base metal, if you want to match your base metal strength, or dissimilar,
Similar metals.
right? So if your weld metal is required to respond to the same post weld heat treatment as the base metal, what it will do, in order to match those strength of base metal, you will use similar filler metal, similar to the base metal in composition, whatever you will be using. Now, in repair kind of welding, uh, it is possible to use the steel in uh, it is possible to use the steel in annealed or over tempered condition. The filler metal does not have to be similar to the base metal in composition for repair welding application. Okay, so for this I will make some note. for repair welding, filler metal does not have to be similar as base metal. BM is base metal, okay? Remember that. Now I was talking about this weldment that must be stress relieved or tempered after welding. Now, uh, in some repair welding, uh, where neither annealing or over tempering the steel before welding, nor stress relieving even the weld upon completion is feasible. So electrodes of austenitic stainless steel or nickel alloy steel, those can be used. So yeah, just remember that or fine. I just made some note. Over here I have mentioned quenched and tempered low alloy steel, high strength low alloy steel, then this heat treatable. Fine. So yeah. Mm, let me take another. Okay, why don't we first do some question and answers and then again we'll come to this theory part. Otherwise that will be much boring. Huh. So tell me what about question one? Choose the correct alloying elements combination present in HTLS steels. So we have talked about this quenched and tempered low alloy steel, you remember? What were the alloying elements over there? If I have this, ah, just look into the slide and tell me what could be the alloying elements. These are the alloying elements even for this HTLA.
Manganese, nickel, molybdenum, uh, chromium.
So you have nickel, monel, chromium. These are my alloying elements for
Option
high
C.
strength low alloy steels also. So option C is correct. Okay. We have done this. We have done this. This one. Just apply your common sense and tell. During the fusion welding of heat treated mild steel, matching and under matching filler are generally preferred for so if you have a butt joint,
Butt and flat.
butt and fillet joints. Right, right. Good. So for butt joint, you have to use similar base metal because you want to match the strength level. And for this uh, fillet weld, there is this I would say means there is no need to match your strength level over there, but you can consider the same kind of same similar order of expansion coefficient, right? So that is very important in your weld structure. So thermal expansion coefficient. Okay, good. So
Sir,
during
here
heat and well, huh.
question fourth, option A and B both are same.
So for butt joints, you want to use matching. For fillet joints, under matching is fine. So there is this respectively.
Okay, okay, sir.
This is done. So for heat treated low alloy steels made using some basic open hearth furnace that should have sulfur and phosphorus percentage. You want sulfur and phosphorus percentage higher and or lower in your steel structure.
Lower.
Right, right. So which one do you think the right one? So if you have this sulfur and phosphorus, so sulfur basically will induce brittleness if you are doing some heat treating in your structure. Uh, it will increase the number of sulfide inclusions that will reduce the toughness of your structure. Even if you're doing some reheating steel with sulfur, that may also uh, that may also result in some tear formation, crack formation, you know. So sulfur and phosphorus will always induce brittleness. So you want to have sulfur and phosphorus as low as possible. So just looking into the options, I want this to be
Option
less
C.
than 0.035. This is the lowest one whatever provided in the question, so that must be less than that. So sulfur and phosphorus are basically byproducts of steel production. Their impurities within the steel. It will always be there, but that should be reduced. Okay, so fine. Next.
हार्डनेबिलिटी इंक्रीज कार्बन इक्विवेलेंट इंक्रीज करने पे if we increase
Perfect.
carbon equivalent in heat treatable low alloy steel increase hardenability increase.
Perfect. So 7 is fine. Next is reduction in tempering temperature of high heat treated low alloy steels, weld joints. Which one is the correct option? So you're talking about this preheating to reduce this cracking tendency in heat treated low alloy steel because they are having higher carbon content. Now the weldment of heat treatable alloy steels is often so you need immediately some stress relieving heat treatment before cooling to room temperature, you know. So during this stress relief heat treatment, the martensite, whatever it will be forming, that is tempered, right? And therefore the weldment can be cooled to room temperature without this crack formation. So we tell this as post weld heat treatment, right? Now, if you are thinking of okay, fine. First, just
Reduction in
concentrate on this
temperature
one.
temperature.
Then I coming to that. So if you are having reduction in tempering temperature, so tempering mean after quenching again you are increasing the temperature to certain level, right? So if you're in reducing the tempering temperature range of heat treated low alloy steel, what that will do, that will increase my tensile strength. So more you increase the temperature, more you are imparting the ductility or toughness
Yes, sir.
to enhance the strength or hardness. So this is the reduction in tempering temperature range,
Yes, sir.
right?
Oh,
So it is true. So yeah, just give me some time for this what I was talking in terms of the thermal history. So I'll sketch something first. So this is temperature, this is time. This is time, temperature. Let's say this is the A1 line, lower critical temperature, and this is MF line. What is MF?
Martensite
Martensite
formation.
finish temperature. Okay, so my heat treatment cycle is something like this. So this is my welding temperature. This is the temperature during welding. And just after welding, you want to do some stress relieving. So what I want to tell over here by sketching this diagram. Yeah. So this is the thermal history during welding and post-weld stress relieving. What I have drawn over here. Now the preheat temperature and the temperature immediately after welding are both melted slightly below the martensitic finish temperature. These two, the preheat temperature and the temperature immediately after welding. And as I was saying, stress relieving, this stress relieving, you will heat up to certain temperature for relieving the stresses. So the
Yes, sir.
stress relieving begins immediately after welding for heat
Oh,
treated low alloy steels.
okay, sir.
Okay, and
G.
this is at a temperature below A1 temperature. A1 is lower critical temperature. There is two temperature, right? Lower critical and upper critical. A1 line and A3 line. This is lower critical temperature, somewhere around 800. I probably lower critical temperature, and upper one is somewhere around 900. You just check in your book. So that must be below A1 temperature. Now, yeah. So the heat affected zone, whatever it will form, that should be cooled to a temperature slightly below the martensitic finish temperature before being heated for stress relieving. Now, if this temperature is above MF, what will happen? This temperature, just after welding the temperature, I have unnecessarily making this FM temperature. this circle what I have made over here. If this temperature is above MF temperature, what will happen? So if you are finishing your welding, let's say still over here, and then you are doing this stress relieving treatment. So I should use some other color. So let's say this is another cycle. The green one is another cycle. You can understand these two lines, red and green.
Yes, sir.
What is the differentiation? One is the temperature just after welding is below MF. One is the temperature just after welding is above MF, and then I am doing stress relieving. So if my temperature is above MF, what will happen? If temperature is above MF, the temperature this I am denoting is just after welding. My recording. If somehow you're finishing your welding at a temperature higher than martensitic finish temperature, there will be this untransformed austenite, correct? Now, if you're having untransformed austenite over there, and you are doing this stress relieving, you are basically again reheating it, right? If you are again reheating it, what it will happen? What will happen? It will decompose into ferrite and pearlite during stress relief operation, or it can transform into some untempered martensite upon cooling to room temperature after stress relieving, है ना? So
Yes, sir.
this will convert to ferrite plus perlite while reheating. Or there will be untempered martensite upon cooling to room temperature. RT is room temperature. Understood?
Yes, sir.
Okay.
Today is last class, sir.
One more. One more.
Okay, sir.
Next Tuesday.
Yes, sir.
This was the
Uh,
postponement of the earlier Tuesday.
yes, sir. Yes, sir. For today is sufficient, sir. Due
Okay,
to
so we had,
Durgastami and Navami.
yeah,
So,
sure. So we will be finishing just right. Just give me some more time. We have finished all those questions. If we have finished, then we will finish up over here. So question 8 is fine. Yeah, it is done, right? Okay,
yes, sir.
okay. Happy puja.
Thank you. Thank you. Same to you, sir.
Thank you. Okay, bye. So we'll be meeting on next Tuesday.
Yes, sir.